Hey, what's up guys? Welcome back to a brand new YouTube video. Today we're going to be talking about universal gravitation. Alright, so the first thing we're going to be talking about is Kepler's laws. So Kepler's got three laws just like Newton, and his laws are basically that his first law is that planets orbit the sun in ellipses with the sun at one of the foci. So an ellipse basically just looks like this, and it's got two foci. And what makes every ellipse unique is that the distance between, we call these radii, but the distance from both of the foci to any one point added up, so let's call this distance r1, this distance r2. r1 plus r2 is always a constant. So for this point as well, if this is r1 and this is r2, r1 plus r2 is going to equal the same number. And that's basically what makes ellipses special. R1 plus R2 is always the same. And what Kepler is saying is that the planet's orbit looks like that, with the planet moving this way, and the sun is at one of these foci. That's all that Kepler is saying. His second law is that planets sweep out an equal area in equal time. So let's say in t time, like, I don't know, a month or something. Let's say in a month, the planet starts here and then it travels to here. Whoops. It travels to here. So how much area is it swept out? It's basically swept out like this much area. Then let's say that the planet's here, and then it again travels for t time and ends up here. What Kepler's saying is that this area that it swept out in t time is equal to this area that it swept out in t time. And yeah, as long as the planet's traveled for t time, it's going to sweep out an equal area. And what this means is, since when the planet's on this side, it's a lot farther from the sun, it's going to be moving a lot faster when it's closer to the sun in order to sweep out the same area. All right, and his third law is that t squared over r cubed equals 1. And it's only 1 for our solar system, but just in general, it's like a constant. It's a constant number. And let's talk about what these numbers mean. So t is basically the period that the planet takes to complete, or the amount of time that the planet takes to complete one orbit around the sun. And r is the average distance from the sun. So we'll prove that later, but for now, let's talk about universal gravitation. So Newton figured out that the force of gravity basically equals g m1 m2 divided by r squared, where if we've got our planets like this, then this distance from the center of each planet is r. The mass of the first planet is m1, the mass of the second planet is m2, and g is a gravitational constant that we kind of figured out around 1700, I think, and the value of g is basically 6.67 times 10 to the power of negative 11. That's what g equals. And we figured that out through like experimentation. So now that we know this, we can actually prove Kepler's law. So let's think about a solar system. All right, we got, our sun here. We got the planet's orbit. We got the planet here. When the planet's orbiting, the sun is pulling in, but the planet isn't getting sucked into the sun. Why? There must be another force pushing the planet out. And this is actually the centripetal acceleration, or the centripetal force. So in case you don't know what centripetal force is, that's basically v squared over r, which is the centripetal acceleration. So then that times mp, the mass of the planet, that's the centripetal force. And since the planet's not getting sucked into the sun, but it's also not like flying into space, the centripetal acceleration must equal the force of gravity, which we just figured out what the force of gravity was. That's gm. In this case, it's gm s, mass of the sun, mp, mass of the planet, divided by r squared. All right, now we can do some canceling. We can cancel the mass of the planet. We can take away the squared and cancel the r on this side. And this implies that v squared equals gms divided by r. And this implies that v equals root gms over r. All right, so we know what the velocity is now, but how does that help us prove Kepler's law? So Kepler's law, let's write it again. It's t squared over r cubed equals a constant. So we know that speed equals distance over time. So this basically implies that the time equals the distance over speed, right? You just switch their places. So if we go up to our example here, let's assume that the planet's orbiting in a circle. What then is the distance that the planet covers? The distance that the planet covers is the circumference of the circle, which is 2 pi r. So this equals 2 pi r divided by, and its speed is v, which we figured out here, gms divided, the square root of gms divided by r. And that squared divided by r cubed. And this r is the same as that r. Because in a circle, you know, the distance is always going to be the same. So let's just erase this. And now we can see that if we do some simplification, let's square the top. If we square the top, we get 4 pi squared r squared divided by, when we square the square root goes away. So that's gms divided by r, and that whole thing over r squared. So now this r is going to go to the very top, and this gms is going to come down here. So then this equals 4 pi squared r cubed, because r times r squared basically equals r cubed, and that's divided by gms times r. Oh, sorry, this is r cubed up here. My bad. Yeah, times r cubed. So then the r's cancel, and this equals 4 pi squared over gms. And that's basically the final answer. So what is this? Is this a constant? Well, yeah, it is. We know 4 is a constant, pi squared is a constant, g is the universal gravitational constant, which is a constant, and ms is the mass of the sun, for which every planet in the solar system, it's going to be the same. So yeah. Now let's talk about gravitational potential energy. So let's say I'm like, you know, let's say we're on the Earth and then a book is up here. It has some gravitational potential energy, right? But what is that gravitational potential energy? So the gravitational potential energy is basically equal to the work it takes to move the book up here. And we know that work is force times distance times cos theta. And we figured out earlier that we figured out earlier that the force was gm1 m2 divided, or in this case m1 and m2 is going to be mass of object times mass of planet divided by r squared times, we know that the distance that the book could move is basically to the center of the planet. That's going to be r. The distance between like the center of the planet and the object, that's r, times cos of theta. So what I mean by cos theta is, say I've got like a suitcase here, and we're pulling the suitcase in this direction, but the suitcase is moving in this direction. This angle is theta. So here, the book could move down, the force is pushing the book down, and the book is also moving down. So cos theta is 0, which means that cos 0 is 1. So then we can basically cancel the r's here, and this equals gmo mp divided by r. All right, so this is our gravitational potential energy, and this works for anything basically. All right, so now let's say I have the object up here, and it falls to down here. So it starts at a distance of let's say r1, and it ends at a distance, this distance, r2. How am I supposed to figure out the change in potential energy? So we know that the change of basically anything is just the, the final stage minus the initial stage. So its final potential energy is with the R1, so that's GMP, MP object divided by R2 squared, that's the final, minus GMP MO divided by R1 squared, because that's the final position. And this is basically going to be the change in gravitational potential energy. Yeah, so in terms of universal gravitation, I think I covered everything. If I didn't explain something well and you have any questions, please tell me in the comments. But other than that, see you next time.